These are probably two very naive questions. Since the clouds play such an important role, the question comes as to air traffic, which apparently in the high altitudes produces a lot of condensed nuclei. And the second is, why is it never considered that we have a thin crust of Earth and then there is this very hot magma below, which produces an immense temperature gradient, doesn't it? And how does this influence surface temperature? Does it have any effect?
Good point. So you're talking about convection in the mantle going from a hot interior and then through the magma, you have escaping. Of course, that, for example, volcanoes are major role on CO2 on 1,000 to 10,000 year time scale. The volcanoes is a major source of carbon dioxide, not on the short time scale. Sulfur gases come out. And that's exactly why during a volcano, you experience cooling, about half a degree cooling. It's been well documented planetary-wide because the sulfur dioxide, it's not from the ash, the SO2 from the magma that goes into the stratosphere about 15 kilometers above the surface. And once you throw material higher and higher into the atmosphere, their lifetime increases longer and longer. The same SO2 you put in near the surface, it'll be gone within a few days to a week. Whereas once you throw it above what we call troposphere, first 15 kilometers, the lifetime goes to 2-3 years. So that is in fact another spectacular validation of our model, seeing how the temperature evolves, and models have done that. So it is a source. I think Professor Crutzen, that's how he launched his reluctant suggestion on geoengineering. He said, we have an example from nature, it seems to work. Paul, I don't know if you want to comment on this.
And the air traffic I was interested in because they predict enormous increases, and I wonder whether this is relevant.
The air traffic, yes. It is hugely relevant because what the air traffic does, it puts particulates and also gases in the upper troposphere. That's about 30 to 40,000 feet. The danger of that, they're not acting like mirrors because the higher the clouds are, the greenhouse effect takes over the albedo effect. So the aircraft produced clouds, in fact, is going to contribute to warming, adding to the warming. But the story doesn't end there. There's also CO and others which come in. So I don't know where that lies in. I don't know, Yuli, if you know, or Mario, one of you can comment on it. It's an issue which is being pursued.
I think there are some limits as to how much it is certainly very important, but there are some estimated limits as to what fraction of the overall signal it can do. But there's a movement, of course, to start using biofuels for airplanes to try to do something renewable. But yeah, it's certainly something to worry about. Yeah.
First of all, a couple of comments. This is regarding the concerns both China and India, which you expressed, and particularly the cow dung use in extensive. It's an important observation. We cannot neglect it. The policy of a government like in India, they have said on one side that they will have a collective but a differentiated responsibility in terms of the greenhouse emission. This has been made clear, and so the country will not exceed in terms of per capita emission, the global emission at any point in time. This is one of the declared policy of the government. The second one is related to the one that was declared by the previous environmental minister, about 25% reduction in the greenhouse gases by 2030. These are two important steps just to illustrate the way in which the government is taking seriously some of the observations that you made. So this part of it, I think, is one step which probably should be recorded simply because of the fact, but this is applicable to many other countries too. The second thing is more a question for you, and this is related to the embedded methane under the ocean, and especially in places like Siberia, the permafrost. And there is a critical temperature at which they say that methane can be released into the atmosphere. And once it starts getting released, it will be a catastrophic way in which it can build up into the atmosphere. And particularly because the greenhouse gas emissions on which you mentioned, this could have a critical impact. And of course, methane's effectiveness as a greenhouse gas is several times more than the carbon dioxide, not even if it is not 10,000 times, I don't know, it could be 10,000, I don't know what number is, but it's going to be. So do you have a critical number, temperature or some parameter which would lead to the release of a large-scale methane emissions from the embedded regions or the permafrost regions of Siberia and other locations? Thank you.
Thank you, Dr. Customer. You asked two questions. The first one is about this differentiated responsibility. I'm so glad you mentioned that. I forgot to mention to this audience, when I said I'm working on the cook stoves to cut down emissions, if we think we in the West, we can drive our SUVs, all we have to give is a few cook stoves to the women in India, that's not what I'm saying. This problem can never be solved without cutting down CO2. And I think of this simply because once you put it there, and as Dr. Molina said, 20% stays for thousands of years. And the other thing, nothing has come out here. The real danger here is the ocean lifetime is about 1,000 years. So if we continue putting CO2 the next 100 years, that heat gets mixed up. It's already there. We can do geoengineering, we can do this. Still, that heat will be coughed up, okay, on time scale. So there is no question CO2 is the most deadly climate gas, and we have to cut it down. My work on the short-lived climate pollutants is I am focused on the near-term disaster, the next 50 years. And I'm finding what people thought is 2 degrees 100 years from now. Depending on where in the probability curve you are, you'll see it 30, 40 years from now. And the only way I see that near-term disaster can be avoided is the short-lived climate pollutants, methane. So going back to your second part of your question, there is more danger on the methane I want to point out. You know that in the US now we are able to get methane from the ground. And the leak from that is a huge issue. We are worried because, of course, in America we want to be energy independent. So the natural gas offers us that potential. But the leak from those, as many scientists have pointed out, could be a major issue. See, the 25% of the increase in the methane, which is about 20 times as effective as CO2, is unnecessary. It's just leaking from pipes, Russia, Central Asia. I'm just thinking, can't we tighten these pipes a little bit better and not prevent this leak? So I think as far as going back to your issue, the permafrost, from the Siberian region, of course, and as you start melting, are we going to get a huge methane influx? And I think that the story is there, no one knows for sure because we have very little observations on that. But theoretically, you can't rule it out. But if that happens, I honestly think it's the end of the story we are talking about here. But I think the one reason I'm really optimistic, I believe my work a little bit more than everything else. And I'm finding, because we are unmasking so rapidly, I think China now wants to cut down its CO2 emission, India is making great efforts to cut down its sulfur emission. Over the next 10, 15 years, the warming will be so large. When I say so large, about 0.4 of a degree to half a degree, that should shut down all arguments. By the time you warm the planet another half a degree, it is warmer than anything we have seen in the last 400,000 years, the glacial interglacial cycle.
much more difficult to do chemistry with it. I mean, to get rid of methane. Is there any, what are the attempts to reduce methane?
One thing I would say, you're on the CO2, you're right that CO2 sequestration is talked about because it's long-lived. You don't have to go everywhere in the world and suck up the CO2. You can just sit here, put a pipe in, and take the whole. The problem with CO2 is not that technology. The issue is there is 1 trillion tons of CO2. That's equivalent to 500 billion Toyota cars circling in the air. Can we find a dumpster to put 500 billion Toyota cars? And then every year we are dumping 40 billion tons. So it's the sheer weight of it. We may need to create another Mount Everest somewhere to put all this. Because we know you can't put it into the ocean. It's choking the ocean, carbon, oxygenation stuff. The methane, fortunately, since it's short-lived, you don't have to suck it from the air. You choke it at the source. Right. For example, in America, the waste dumps is an enormous source of methane, and we know how to. It's costly, but not as costly as CO2 extraction. And we take the methane and use it for energy. And the natural gas pipes, of course, we have to upgrade all these natural gas pipes. So that's a second source. Third is cattle.
Cattle, of course.
And Paul has to be, it's mainly coming from burping, right?
Yeah, sure.
I mean, our genetic GM modified friends can come with some crops to prevent them from burping so much. I'm not joking. These are all doable issues. That's why you're pushing the SLCPs. And so we can go down the list. We have come up with, in this United Nations study, I was the vice chair of it, including with YASA, we considered 2,000 measures and distilled it to 14 measures, which people can do now. And the beauty of this short-lived climate pollutants, the benefit accrues to the region which does that, because it's short-lived, it's locally concentrated. For example, if I cut soot emissions in California by cutting out diesel, we get the benefit first, health benefits. Same thing, the cook stoves in India, the women get the benefits first. So there are multiple things here on this. So I would say, from a chemist perspective, CO2 is simpler, but from a climate perspective, I would choke the methane at the source. Mario has.
Can I just make a brief comment on methane also, because there's, as you know, a very big change in, particularly in the United States, with gas prices, with shale gas. And so this large increase in the use of natural gas, which is mostly methane, might be worrisome. But the perspective there is, if you use it to replace burning coal, then you are improving the situation, because for the same amount of energy that you get out, electricity and so on, you emit half as much CO2, because methane has, each molecule has, of course, 4 hydrogen atoms and so on. So that helps, but in the long run, it's still just a transition fuel, okay? But it's, geopolitically, that's the word, important for North America to become energy independent, and fracking, which is a way to use shale gas. If you do it properly, you don't get leaks, but you have to do all sorts of things so that it's not a major environmental issue. And the other, now, a very brief comment, it's interesting, but it's the per capita use. That's indeed important to take into account and so on, but I thought about it for some time, and my colleagues at Princeton, particularly Rob Sokolov and Steve McCallum, they have a paper which I had agreed with them. You have to do that carefully, namely, not use a per capita argument in a large country like India and China just to continue increasing emissions. So it would be good to also consider the per capita emissions taking some measure of the distribution of wealth, okay? So that you make sure that the people that are earning more and increasing in their standard of living and so on, that they improve their energy intensity. And China, of course, is making commitments to do that, so that it's not just at the expense of the people that don't use much energy, but that the whole society begins to improve and we don't function in the future the same way that we have functioned in the past, and yet we still strive for a better standard of living.
Can I just comment? That's exactly the reason why I said the second point. We have a target of reducing the energy intensity, improving the energy intensity by having a 25% reduction in the greenhouse gases by 2030. That's exactly the reason why I qualified the first statement with the second one.
Very much agree. I wanted to emphasize.
I want to return to the question that Dr. Singer asked about the subsurface magma. Now, you responded to that question in terms of things like volcanic activity, but we know that there's a temperature gradient as we go down into the Earth. There's a temperature gradient, and a naive analysis would say that if there's a temperature gradient, then there's a heat flow. So the question that I have is that just simple heat flow, leaving apart volcanic activity and the ejection of particulates into the atmosphere, just the simple heat flow from the interior, is that an important part of the heat balance equation, or can we ignore that?
So much. I blew that question then, if that was the issue. Yeah, it's about, globally, when you integrate, the heat flow from the Earth is about 1/10 of a watt per meter squared. The sunlight is 240. The greenhouse effect is 3 watts. I think so. It's a much smaller component over the whole scheme of things. But of course, that's important. That's why when I go to Scandinavia, they use geothermal heat to heat themselves, because there is a seasonal difference. It could be, I'm annually averaging everything. But at the same time, one other issue that raises me, I needed to quantify, there's a lot of thought and suggestions. Solar radiation is driving a lot of the climate change. I wanted to briefly address that. The Earth radiation budget experiment I talked about was the first time well-calibrated solar radiometer was put on space. Before that, we monitored from surface. And that, now we have continuous data sets for 30 years, 3 solar cycles. And the amplitude of the variation with sunspot is about 0.1 watt per meter squared again. So I turned the argument to the surface. If 0.1 watt can drive so much of climate change, imagine what 3 watts would do. That's 30 times large. Then they turn around and say, no, it's due to some exotic feedbacks in the ultraviolet, in the stratosphere. And that's where I want this community to know. Those who claim solar is driving climate change are invoking more unknown exotic feedbacks than climate scientists. We are mainly thermodynamic, physics, thermodynamic, chemistry arguments. And in fact, the Norwegian group, which has pushed the solar so much, you ask them, their argument, the starting point is very correct. When you have sunspot cycle, although the total variation is only 0.1%, in the UV, it's 10 to 15%. It's larger. But the UV doesn't penetrate to the troposphere. So it has to do something mysterious in the stratosphere. Of course, it impacts ozone. But we know the ozone change is about 5%. If 5% ozone change can drive this major climate change, such as tropical storms, we are in a lot more trouble because we are talking about magnitudes of changes which is 10 times large. And anyway, thank you. Thank you.